content on the screen. Even you can go through this. I will take another problem from my notes point of view, which will be very easier for you. So this problem is dictating you the statements, and handouts are there, or individual stepwise solutions are also there on the screen. I'm just making it to stay for a while, and I'll be able to discuss the next part of which how that particular problem is visualized to solve. This can be viewed from your video. You can just get through this particular problem as well, which is a very simple problem, very small short time based problem. Now moving to the next problem which I wanted to share to you is today is from my notes viewpoint. I will just take it up. I hope my screen is visible to you. The handwritten page which I'm trying to project you is visible to you. All of you, please.
Yes, sir.
Yeah. What I will do, I will reduce the screen so that you can use a maximized view of that. Okay. So I just make it, I read it out like this way. A single area consists of two generating units having following characteristics. Unit 1, a capacity of 600 MVA, whose regulation is 6% on unit base, means this percentage regulation is on unit base of its own 600 MVA. Unit 2 is 500 MVA capacity, 4% regulation, and this 4% is defined on its capacity. It's called PU on unit MVA base. On its own capacity, it is a rating. These two units are operating in parallel and sharing a load of 900 megawatt at a nominal frequency. So these two were put in parallel for 900 megawatt, and nominal frequency is not mentioned here. At the end, it is mentioned. Unit 1 supplies 500 megawatt and unit 2 supplies 400 megawatt. 500 plus 400 is the net load, 900 for me, at 50 hertz. So the nominal frequency now it has come as 50 hertz. A change in load by 80 megawatt is noticed. A change in load has occurred by 80 megawatt. What is our requirement to solve? The first requirement to solve is find the steady state frequency deviation, delta F, and new generations on each generator unit. Nothing but sharing of those units whenever there is a change of 80 megawatt load. For a change in frequency, how is that set point on each generator change? Assume that there is no frequency dependent load. Can you see this statement? Assume that there is no frequency dependent load. D is 0 over here. That is part A. Part B says, for the same problem in a area 2 generator having certain characteristics, sharing a 900 megawatt load, suddenly experience a 80 megawatt change. How is that share without having any frequency sensitive loads? Was the first part. The second part is the load varies 1.5% for every 1% change in frequency. See, value of area's damping constant is not mentioned by a D equal to, it is spoken by text. How is that? The load varies 1.5% for every 1% change in frequency. That itself is the definition of D. D is the percentage change in load for a percent change in frequency. It means 1.5 is known as value of D. It is the 1.5% change for every 1% change in frequency. So D stand here as 1.5. This is how you have to extract a value of D. if it is a text convey like this way. Find the steady state frequency deviation delta F and new generation on each unit. The contents are just a marginal change, but requirements are same. What is the new frequency? Nothing but delta F we have to find out. New frequency I have to find out. Delta P1, the share. Delta P2, the share of machine 2. So both I have to calculate in respective steps. For that, what I'll be doing? Choose 1000 MVA as base. It's very clear because this one machine is having 600 MVA capacity, another is 500 MVA capacity. So their droops are presented on their own capacity values. Then it becomes very necessary for us to take them into a common base to solve this problem. Therefore, what is mentioned here is choose 1000 MVA as base. So this I must keep in mind. I should not simply solve given a value and go ahead and get stopped. No, you have to find if there is a change in capacity, definitely there will be a new value given. So therefore, we should be careful. New base is 1000. Now the first step is these droops I have to shift to 1000 base from 600 and from 500. That's what is being done. R1 is 0.06, the value of the quantity, new base value divided by old base value. So because this is a percentage, it is put in fraction into new base divided by old base. I am shifting it to 0.1 per unit on 1000 MVA base. Similarly, 4% droop on 500 MVA second machine. To shift it to new base of 1000, what we will be doing? New base value divided by old base value into value of the quantity. It is 4%, 0.04 fraction 1000 divided by 500. So 0.08 PU. Now change in load. What is the change in load expressed here? 80 megawatt. 80 megawatt divided by 1000. It becomes 0.08 per unit. So this is how the first prerequisite of this problem is to convert them on a common base. This is a very basic. If it is ignored, whatever one page of work what we furnish later will not be a valid one. So therefore, please consider carefully if the different ratings are there, choosing to a common basis must. You may ask me, by chance this is not mentioned. By chance it is not mentioned, it's a grace. Or else at that time how to work, somebody may ask, let it be a grace, but how to begin? For you the simple thing is, one of this you can take as a base value. See the logic here. If common base value is missed in the problem, how people work? People work. You can see some books if you find convenient. One of the value is taken as a base. That is the initial way. If I take a 500 as a base, this will be 4%. This will be converted to base of 500. This 600 divided by 500 into 0.06 is the converted value of this to the 500 base. Like that, people have a practice of converting the non-similar values to a common base value. So I'm quite sure it will be given all the time in such way. If it is given, use it. If not, also I have given you a clear instruction. One of the value can be taken as a common. You can convert the data into other and solve. So then once I calculate the PU, I'll be having frequency deviation experienced when there is a dip or change of 80 megawatt load as a 0.08. So I have minus delta PL divided by 1 by R1 plus 1 by R2 plus D. D is missing here because the case A is what? Area is not having any frequency sensitive load. Part A is saying that no frequency dependent loads are viewed in the area. Then D is 0 here. Absolutely D is not written here. Then I will mention the values. When I mention, this is the frequency deviation. So this frequency deviation is 0.00355 per unit. Because all these quantities are in per unit, it must be in per unit. Then the steady state frequency deviation equal to 0.00355 into 50 in terms of hertz. In terms of hertz it is. Now, what is the prevailing new frequency of combination of this generator? It was originally said the line frequency was 50, base frequency was 50. It was here. Can you watch my mouse cursor, which I'm hovering here. 50 hertz is the base frequency. Now this frequency get diminished marginally, that is by a value 0.177 hertz. You will find 50 minus 0.177 as a 49.82 hertz is a change in frequency. Now, once there is a change in frequency, definitely the combinations of these two generators, which are sharing the load, total 900 megawatt was shared by these two. One was sharing 500, another was sharing 400. Now, due to 80 megawatt shift, what is that new share of P1, P2 total? I want to calculate the reflection for 80 megawatt. I would like to do first. That is how minus delta F by R. What is this exactly? This ratio? This ratio is the pickup taken by the generator 1 with the droop nature of that. So this delta F contains the effect of change in load. What is delta F? Delta F is delta PL by ratios of that. This figure carry the reflection of load on the system. This is used in the equation to see proportionate pickup by the generator as a droop relation. So this is how interestingly it is connected. Delta F is reflecting the load in terms of frequency. That drop is reflecting with the droop by the value delta P in the machine 1. So this is how this is connected to delta F by R1. Then I will locate the content carefully one by one. When I locate the content 0.00355 divided by 0.1 after converting it to per unit, this stand as 0.0355. I sincerely suggest you people, whenever you are working on per unit value, when you convert back to actual megawatt, probably the decimal point and later, you observe my point here, 0.0355. Why I wrote so many significant digits after the decimal? Because when I multiply a base of 1000, at least I must be able to see readable digits. Therefore, working decimal point and later by at least 3 significant digits is really required. It depends. If the value is so narrow, make one more digit. So like that, please think this scientific fixing of decimal point and right side content of that carefully you please work. Because in this problem, I am going to show you very marginal change is going to occur when I add them. Whatever is that. Let's see. This is very small value into 1000. You can see here. If I multiply it by 1000, I wrote in the corner here. It becomes 35.5 megawatt is the share of machine 1 out of 80 megawatt demand shift. So that is called 35.5 megawatt. Similarly, machine 2, if you want to check it out, what is the machine 2's share? Again, delta F divided by its droop. Its droop, you can see on the page top here, 0.08 pu, 0.08. It becomes 0.044 pu. So again, there are so many significant digits are there, which I did not wrote here. When it becomes necessary for me to multiply 1000, in the calci, I pick them again here. It becomes 0.044375 over here, hidden here. So when I multiply by 1000, I ensure better to present 44.375 megawatt. If I add them, they should be very close to 80 megawatt. I wrote it at the corner, left corner here. Delta P1 plus delta P2 equal to 80 megawatt. This is how very simple problem with the D0, I can get P1, P2. Let's see how it is being processed in the next page. In the next place, unit 1 is expected to supply now. Old it was supplying 500. Now it is 35.5 additional. 535.5 is the new load on machine 1. Similarly, I have 400 plus 44.375 from machine 2, which is 444.375 megawatt. The revised frequency of this combination is 49.82 hertz. This is the outcome of part 1. So this is what is asked in the part 1. Can you see here? Part 1 was demanding you steady state frequency deviation, new frequency, and share of each. Similarly, second is demanding you for an area's reflection of D equal to 1.5. The same thing I have to repeat with the D equal to 1.5. You can see here. When given D equal to 1.5, what is the deviation experienced? Deviation in frequency experienced is minus delta PL by 1 by R1 plus 1 by R2 plus D. This is visualized to you. Now you must be very careful. So this D is given 1.5. So directly I am using it. It is specific to a area. So it is 0.08, 1 by 0.1 plus 1 by 0.0 plus 1.5. Directly it results me 0.00333 per unit. So the steady state frequency deviation in a case 2 is so much by value into 50. If I do, it become 0.1666 hertz. If I utilize this to get the new frequency, 50 minus this value refers to 49.833. So there is a little superior frequency compared to the old frequency. Can you see over here? 49.82, here it is 49.833, something like that. So this is the change due to reflection from frequency sensitive loads. Now, because of this changed frequency or due to frequency deviation, what is that pickup taken by generator 1, generator 2? Again, you should be very careful. Generation pickup by 1 it should be less than what it picked in the previous part. Generator pickup 2 is again less than what it picked up in the previous part. The difference is because of the rejection of load due to frequency deviation. That I will again prove you. So delta P1 is delta F by R1. I calculate and I will show you the fraction into 1000 as 33.3 megawatt. 33.3 megawatt is the pickup from machine 1. And machine 2 pickup is again delta F by R2, which is 0.042, something like that, 42 and a fraction here. 0.042 pu into when I multiply roughly 42 megawatt. When I consider these two, 33.3 plus 42 rounds off 75.3. But what was my load? 80 megawatt. Then who bear this difference 80 and 75.3? 75.3 and 80, the difference is nothing but the rejection of load which is from the inductive perspective. What is that? Let us see here. I wrote here in the statement, the drop in load due to change in frequency. You can see here, the drop in load due to change in frequency is given by delta omega into D or delta F into D. So it is delta F, whatever is calculated in this part. What is the delta F in this part? Delta F is 0.00333. This is the delta F. Delta F into D. What was D given? 1.5. If I multiply this, this is called frequency sensitive load reflection. That is 0.00499, something, a short fraction in per unit. And in megawatt, if I multiply by 1000, I'll be getting 4.995 megawatt. Now you see this 4.99 megawatt with the 75.3 some megawatt of share of these two. If I add these, it results me nearly 80 megawatt. Now you will see 4.995 megawatt is actually loaded lesser to the generator. It is because of the inductive loads which were absorbing earlier in the part 1 study. Now due to drop in frequency, they started absorbing lesser. By what value? 4.995 megawatt. So this 4.995 now became relief of generation for the generator. It would say their generation set points were relief by what value? 4.995 megawatt. That is the reason you will see first generator contribute 33.3 megawatt, second contribute 42 megawatt, together 75.3. If you want to see, I can go back and show you what was the contribution for the machine 1 at that time. Machine 1 was contributing 35.5. Machine 2 was contributing 44.375 when D was 0. Now 35.5, you observe here. What is this now? 33.3. Is it not a relief for this generator? This is generating lesser than what it was generating. Why so? There is a drop of inductive loads here. And it is 42 here. It is 44.375. So second generator is also experiencing a short relief of generation. This relief of generation is because of the drop in load due to inductive. So this may happen due to loading effect. Now can you imagine at this point, anybody is having a question in their mind. If frequency increases, what will happen? Suddenly, an industry shut down abruptly due to a heavy fault. Suddenly, so much of megawatt power what that industry was consuming suddenly shut off due to so many internal things. Then that megawatt load is additionally floating on the system. What will happen to the system? Definitely load relief is experienced by the power system. By the relief of load directly, what is your observation? Directly frequency shoots up. Delta F, what I am calculating here is on loads 50 minus whatever the quantity in this example. It may become 50 plus that extra quantity. Then what is the effect of that? The line frequency become superior. Because of that, what will happen? Just imagine. Because of that superior frequency, no doubt there is a proportional change in these things. Proportional change in megawatts by P1, P2. Also, I am serious about this. Delta omega into D fraction. This will be at the time and a higher load here. So you can see this delta omega into D. This makes the things that they will start absorbing more. They were now relief. There is a relief of load when there is a drop of frequency. Exactly contrast phenomena occur. They start absorbing more and more power from the system, which is having higher floating energy in the system. So therefore, frequency has very detrimental effect. You might recall my statement. Frequency deviation within a range is permissible. Certain frequency and above, if there occur a oscillation, it's a very detrimental to the connected system. One statement I cited long time back. So therefore, it should be seen carefully. When loading occur, rejection occur. When there is a relief of load on the power system, frequency becomes superior. That will make inductive load to XL, 2 pi FL, directly proportional to the frequency. They start absorbing more and more power, make the system unhealthy at that time. That should be the observation from the particular point. So you must be careful to view this in a differential way. Let us take another view on this. Okay, I'll be again back to the screen. Hope my PowerPoint slide is visible to you all. May I consider this is visible to you? May I consider this visible?
Yes, sir.
Yeah, thank you. Now, after having seen the problems of variety 1, 2, 3 like this way, let us see what is that ALFC by control system block representation. Complete model of automatic load frequency controller. How exactly this controller control? You have seen some simulation. When I was working with the Power World simulation, I have shown you in a area when a load occur, increasing load or decreasing load, how is that generator cope up that demand to see to that they address the load, keeping the frequency and voltage in stable way. If such two areas are interconnected, how is that delivery of power to the neighbor corporation, interaction among them whenever coordinating themselves occur? Then what is that exactly the control system block functioning in a area I would like to project? That's called as complete ALFC model. So ALFC model refers to automatic load frequency controller. This is going to adjust the input as and when there is a drop in frequency or a change in frequency, so that that block is represented as first block of that. Let us see a governor. We will not go as per this line out. Let's see, you require a governor which regulate the input to the turbine. First block, which governor regulated displacement, control the fuel to the turbine. Then I have a turbine block. Turbine which give mechanical energy to drive the generator. Each the fuel, whatever the kind of fuel it is absorbing to drive the turbine, it will drive the generator shaft. This particular turbine combined to a generator will be having a transfer function that we have a generator plus load that is delivering power to a locality. that locality when connected to a generator definitely load the system. There will be a drop of frequency of that. It means to say generator and load, turbine and governor are connected one to one in the block. Like that, governor is represented by a first order lag function. First order lag function a block. For that governor, what is the stimulus? Stimulus for the governor is request reference set point. Reference set point means suppose the governor has to function 0 to certain displacement x value. Who is that? What is that x value? X is the limit, minimum of 0, maximum of x, within which governor can change its operation to open the wall, close the wall. That x is called pre-reference. That reference is set by some authority that is coming as an input to which that you can see delta p reference. Delta p reference is the speed set point. For this, I want you people to imagine the fly ball governor mechanism where you had reference point setting. That reference point setting become an input to the governor, and governor function from minimum to the reference set point, and it will give displacement of that as a change in position of the valves. The change in position of the valve will definitely make increment or decrement of fuel to the turbine. Then it become a turbine. Turbine is again represented by a simple first order lag function with the 1 by 1 plus STR, turbine time constant. So this turbine has an input which is displacement of the valve, which make the fuel control to this, will transform the mechanical energy into mechanical delta PM, or this valve displacement provide mechanical supplement. So this is going to transform the input displacement of the valve into mechanical output. So this mechanical output nothing but driving the turbine to driving the generator. So this generator and load together represented by a 1 by 2 HS plus D. So we know that the load in a just you function view this much only. In a locality, when you have a generator connected to a load may be delta PE. Delta PE refers to total electric load, in which we have frequency insensitive, frequency sensitive loads. So therefore, delta PL refers to a minor change in frequency insensitive load, and D refers frequency sensitive loads of the locality. Together, this right hand side representation block refers to generator and load together, and for this demand is electrical demand and areas reflection by D. So this will be getting an input from mechanical part and the load on that. This difference play on this generating area, transform it as a delivery to variation in frequency. Therefore, each transfer function block have their input and output values respectively. Like governor has reference point as its set point. Again, we'll see what is this feedback very soon. This need a stimulus that is called reference point to whatever the set value is there within which it will work. If set point is to be changed, this will come in picture. So this governor will transform the request power displacements into physical distance or displacement of the valve by its transfer function called first order lag function. And the turbine takes this variation in the valve open close as mechanical input supplement to that. Valve means resource control. This resource will definitely accelerate or decelerate turbine to develop the additional mechanical input to the generator or regulate it. That's how this transfer function, turbine transfer function, on the change of valve position, develop the differential or change in mechanical input. Therefore, this mechanical change in input is because of the change in electrical loads, either in insensitive or sensitive load. Together, try to suffice the requirement of the locality. So therefore, this generator and the load together transform this difference, that's called delta PM minus delta PL input to this transfer function into deviation of frequency in that area. So this deviation frequency need to be again addressed by the governor. Governor has to see to it that this frequency deviation must be addressed to 0 or permissible. Then this error is fed back. Error is fed back by droop nature 1 by R. R refers to the governor's droop reflection. So frequency deviation delta omega divided by R is fed back to the summing block here. Then what happens at the summing block? What is set? Request power setting minus the actual power which is being thrown out, called as delta omega by R. That is difference. Delta P reference minus delta omega by R become power displacement or error to be considered by the governor to change the valve, and this change in valve make the change in mechanical input because of this frequency error. See how they are connected one to one. So this frequency error deviation is fed back to the input block here in this first governor block. How do governor adjust it? Governor will take a request from the reference set point. If the reference set point, which is set originally, makes the requirement of these things fulfilled, then this delta omega must be 0. Delta omega is 0 means what? Error is 0. What the frequency is appearing is actual required frequency, and it must be meeting the loads perfectly. If there is a error available, delta omega is noticed, then this error has to be nullified. To nullify this, it has to be fed back as a feedback path to the reference set point. What was the reference set point? To that, a correction from the error delta omega is fed back here. It means what was the original set point which made everything perfect, due to change in loads, this error is noticed. This error is noticed from this generating plant and load area, that is causing either delta PL to occur or D to change its impact. Because of this block's reflection, delta omega is resulted. This delta omega is to be addressed by the turbine by giving mechanical input to that. Then how can turbine give a mechanical input to that? If it is controlled from its valve positions. How do valve will open to supply the additional input to the turbine? They require governor to act. How do governor act to displace the valve? It will get the correction its input. How do the correction over here comes? The feedback. See how the sequence is connected. So error makes every block to go reverse, and think, what is the error here? Why this error has come? Due to loading phenomena. So because of this, deviation is noticed. This deviation is to be addressed by what? The mechanical input. The mechanical input in the turbine need valve opening. Who will open the valve? Governor. How governor operates? By input change in its terminals. How do input will change here? By the error setting here, whatever the error we have here, we have to transform delta omega by R as power displacement and set point, actual value and the set requirement. Error has to be input to the governor, and governor will take care of shifting it, either open the valve or close the valve. Suppose there is a drop in frequency. Let's say frequency 50 hertz, it has come to 49. So there is a 0.1 drop here. Let's imagine frequency has reduced here. Delta omega is say 0.1. This is to be made 0. This 0.1 error is fed back. What is the power actual? 1 pu. 1 pu, and this error is taken as stimulus to governor. Governor will make valve to open. When the valve is open in proportion to the error here, definitely additional input to the turbine makes the mechanical supplement delta PM to increase. Delta PM increases because of delta PV noticed. So this is a transfer of this transfer function. So output by input is the transfer function, whatever we have here. So output increment will come whenever there is an increment or a change in input. So this increment will come or change will come whenever there is a need for the correction. The need for the correction come whenever set value, actual value are not meeting your requirement. So this feedback path is active at that time. All the time, this keeps on correcting the requirement. This summing block always corrects increase, decrease, increase, decrease within the range this feedback is being provided to this. This way, governor will shift this error available over here as a change in set point to a displacement. This displacement will correct the turbine output here. This turbine output and loads whatever have changed, difference of these two acting on this transfer function change error to 0 or keep deviating. Therefore, this is how this block, the deviation in frequency is continuously monitored and fed back to the system to address this deviation to 0. Now, this is how the functional block diagram is interconnected in ALFC. This is the first block diagram. Still, we have one more revision for that's called as integral controller has to be done. How do you feed this error? Well, I'm just feeding directly here. Is it really necessary to that some other control is required? Yes, definitely required. So first block diagram which we find is feeding the error back by droop nature. Then it become necessary for us to understand how the reduction of this block diagram takes place. So we can see here reduction of this block diagram is delta omega, because it should be in Laplace frequency domain, delta omega s, delta omega of s. Can you see this? Delta PL of s. So output and input, output, input here. This whole block comes in the feedback path. Delta omega s 1 by r and feed reference acting on this become feedback path. Now this must be my input and this must be my output. So I can say output delta omega s deviation equal to minus of delta PL of s into whole transfer function. How is that? 1 by 2hs plus d in the numerator, 1 by 2hs plus the forward function divided by this block 1 plus this already the negative feedback 1, because this is the negatively fed feedback. This is 1 minus of minus means 1 plus 1 by r first product. Next is 1 by 2hs plus d into 1 by stg into 1 by str. So all these three 1 by 2hs plus d into 1 by stg into 1 by str. So already 1 by r. This become the representation of the block, which I simplify further. You can see here. So when I take this LCM and make it simplified, so this simplifies as minus delta PL of s, the numerator and denominator. You can see here. This on simplification 1 by str, 1 by stg, 2hs plus d. When I make it common, it become 1 by r, 1 by r multiplication of all these terms in the other side. You can see here 2hs plus d in the bracket and outside bracket one more 1 plus stg and another bracket 1 plus str plus only 1 by r. Entire term go to the numerator and numerator term comes denominator. 2hs plus d, 2hs plus d cancel away. What remain in the numerator is only 1 plus stg, 1 plus str. Can you see here? 1 plus stg, 1 plus str, and this denominator got simplified. So this is how the simplification is taken up here. Now this transfer function, when I rewrite it, delta omega s divided by delta PL of s equal to this PL of s taken other side. So it become 1 plus stg into 1 plus str divided by 1 by r plus all these terms. Now some book refer on replacing the gain of the transfer function or gain of the power system as 1 by d. Here I have h as an inertia constant, d as a area damping constant, r as a droop nature. Using these substitution in this way, kps, the gain of the power system 1 by d, and time constant of the power system 2h by d, this 2h by d, by replacing as a tps and kps, I have simplified version of the representation. It means wherever I have d you take down here, 2h by d is outside. Okay. Similarly, this particular representation tps by 2h by d, kps equal 1 by d. This whatever the term I have taken here, d if I take common and make it a numerator, what will happen? 1 by d become kps. So here 1 by d become kps and kps by r. So here comes 1 by d. This 1 by d, when I take d outside here, so d has to come over here. 1 by d, 1 by d equal to kps by r, and d comes out, and wherever there was a tps possibility, I substituted tps here. It means replacing this hsd in terms of times and gain, that's being done by this function. This is how this will make the shift in this, and we can revise this as a transfer function of the ALFC model. So we can see KPS and TPS are calculated with the D expressed in per unit. So why I took this? There can be a presentation required, complete ALFC model with the transfer functions. Then this is required for us to understand how this functions. Then for this, if I see another simplified view of that from different books, it is again P reference, governor model, turbine model, and the load model. Why I took this, you might ask me. Here you can see ms plus d. Earlier I had 2hs plus d. 2h equal to 1m in inertia representation. Both are inertia constants. So replacement of h is done here by m. Hence I took this. So you might find some books representing this way, some book representing in this way. This is by Dr. K. Umar Rao textbook. This is from Wood and Uhlenberg textbook in the reference area. So that was one of the premier book. Hence I took this also to put you how the transfer function of this ALFC or generator complete model is viewed by representing governor model, prime mover model, and feedback path, and load and area. Then here you will see again 1 by 2hs plus d is put as ms plus d and all other functions. This is another transfer function representation. So therefore this should be seen as a transfer function of the ALFC. Now from this I have something to say, steady state analysis. During steady state, how this ALFC is going to behave. For that I have one simple approach called as steady state analysis of ALFC. For this delta omega s equal to minus delta PL and transfer function I have here. So how it is being done? Using final value theorem. So if now there is a step change in load, so that delta PL of S become delta PL by S. Step means 1 by S. What you do? We can obtain steady state frequency deviation, which is delta omega SS, we write steady state from final value theorem. Then what will be done? Delta omega steady state equal to limit S tends to 0. S into delta omega S I have to calculate. Limit S tending towards 0. S into delta omega S I have to calculate using final value theorem. When I substitute delta PL of S by delta PL by S into TS and limit S tends to 0, when I substitute, just see how this delta PL of S and all this transfer function become here. It means this is represented here. We have to say S equal to 0. I just go back here, S equal to 0. Wherever there is a S, 0, 0, 0, 0. I go back here again in this function. Just see transfer function of this one, TS. So S equal to 0, 0, 0, 0, 0. You substitute. What you get here? The only constants of this will be coming up. That's what is being written here. It become 1 by R plus D. All the other S operator term goes off. Therefore, this transfer function automatically become 1 by R plus D. Therefore, frequency deviation at steady state. Steady state frequency deviation is delta PL into 1 by R plus D. This we call as minus delta PL and area frequency bias. Beta is representing 1 by R plus D, area frequency bias. If there is no load sensitive to the frequency, if D goes 0, R go numerator. You can see delta omega S is equal to R into delta PL. That's all. This is called steady state analysis of the ALFC, during which we will find frequency deviation as delta PL by 1 by R plus D. Then when D is 0, automatically it become R into delta PL. This is one extension, steady state analysis. The same thing I have one page here, which is one more slide, which is here. I'll just show you here. Steady state behavior in a different way. Delta omega steady state equal to S into delta omega S S tending to 0. The same function. Wherever there was a S, S is put 0. So you will find delta PL 1 by R plus D. This is what I have. So steady state behavior. This is what the equation we have referred. Delta F equal to minus delta PL 1 by R1, 1 by R2, 1 by R3 plus D. Whatever the equation I referred for solving the problem. That's called steady state behavior. During the steady state behavior, this was the equation we got. So we could use it already in the problems. So this is how the steady state behavior of the ALFC model can be visualized. Next, moving to another simple concept, which I would like to show you here. Where is that? This one. Proportional integral controller. What is this exactly? Now just observe this. You can observe either upper diagram or lower diagram. This is actually a P reference. However, it was in the earlier case study. It was there. There was a summer block. Yes, summer block is there. There was a governor block. Yes, governor block is there. There was a prime mover block. It is there. And there was another correction block here by load and mechanical input and area response. And there was a feedback path originally. This was what we have seen already by this time. Now, there became a necessary path for second feedback. Can you see this second feedback here? This is what I want to present now. Proportional integral controller required to change the set point of the governor. Earlier, we had ALFC. Whatever the ALFC we have just discussed was called as open loop controller. That was having only one feedback path. That is called as primary controller. Now, that was not at all sufficient. Now, I will recall back. What is ALFC? ALFC is a automatic load frequency controller. Has to see to it that as and when there is a change in load, frequency drops. To supplement the drop in frequency, it has to increase the mechanical input to the turbine. As well, it should see to it that RPM of the turbine is managed properly. That is supplementing the mechanical input, primary part of the ALFC closed loop. That is the two important closed loop of a generator we have seen, AVR loop and ALFC loop, in which primary loop of the ALFC I am touching. That is only to supply mechanical supplement to the turbine. The speed feedback was referred. So that speed feedback work and make the mechanical supplement to the turbine. That was the primary. That is represented by first upper half of the representation. That's called speed or frequency droop. By droop, it is feeding back. May, that is to supplement the mechanical power. Often, it is not sufficient. Then what is required? The direct shipment of reference point by the sense of frequency by integral controller has become very necessary. This is introduced to change the dynamic behavior. It means to say the certain changes what would occur here should be reflected directly at the set point, so that governor and associated prime mover will change their mechanical outputs such that subsequent change in frequency is addressed immediately on the need. For that, it necessitated use of integral controller in the input block side, that we call as a PI controller, proportional integral controller, feeding the frequency deviation back to the reference point. Now, what is this exactly doing? This is taking the error. This is going to amplify the error, like your gain of KI, like a K over here. Then add it up and integrate it. Integrating means accumulate those things, amplify, integrate, and get the set point revision here. That set point revision and the actual droop by power calculation together modify the input to the governor turbine system. These two are multiplied together, simplified block here. So this is in need of proportional integral controller. So what do you mean by this? Let us take one more view here. I go back and tell you. Before going to the next problem, it is necessary for me to interconnect to you. This was having only primary loop. It was only pre-reference, governor, prime mover, and area response, and back to this. This was the only part. Now, along with this, additional extra path is provided to the input side here. Now, why this is given here? Now, I'll take you back to the first slide of mine. So there I have a lot of information for you to get to that. So come back to this point. So here you have a generator, you have a feedback, and this feedback, you just observe here, this feedback is taken up by the governor and turbine mechanism and to change the mechanical input such that generator cope up for the requirement. Now, what is this P reference set point? P reference set point is an authority fix the set point for the governor so that governor function from minimum to P reference. This P reference set point is done by an automatic generation controller, AGC, which will limit this, mark and seal it. Within that band, governor will function. Who will be doing this? How you will be doing this? That is what I am trying to convey. This become automatic need for the requirement. Therefore, the frequency what we have on the line, generator output power, the frequency deviation is taken from the frequency sensor and it is mixed with the power. So again, I'll go back here. See here. So there is a line frequency measurement, line frequency sensor. This line frequency is brought here and this signal mixer will transform this into a power signal. So I am coming back to the first day discussion what we did. So what the power this generator is transacting and what is the line frequency what it is having, and this is transforming this as an area control error. This area control error nothing but an input to the integral block. This integral block which I am speaking now, integral controller, PI controller, this will magnify the error, apply a gain of KI, whatever the integral gain, amplify it and accumulate it as an integration and set it as an speed changer point. Set it as either to reduce the speed set point or increase the set point. So this block has become very, very necessary. Whatever we have discussed all together is only this part, only this part. Whatever the controller I was discussing as on the point was only ALFC, but only this block. Governor was functioning with the limits, that's all. P reference has come here. P reference has come, this was functioning. Now, who will modify the P reference? Modification for the P reference is secondary control loop of ALFC. Secondary control of ALFC means you can see the flower bracket here. This is the flower bracket scope. Here I have extra blocks here. So these extra blocks do take care of this P reference set point. For this P reference set point, what is the requirement of control is frequency. So I am necessitating that this is very necessary to take a line frequency feedback as well as the power what it is transacting, transform that into error. If the system is not having any frequency deviation, definitely governor is not in need of any change of P reference here. Whatever I am speaking about P reference, it won't call for change here. If governor is meeting the requirement, there is no requirement of change here. If governor do not fulfill the requirement over here, deviation is still noticed, then governor stall. It cannot perform better than what it is right now doing. Then revision of P reference is very necessary. This revision of P reference is done by supplementary loop. That supplementary loop utilize integral controller. That's what I wanted to scope. So supplementary control require integral controller. This PI controller is taking signal from line input or line power as a frequency feedback. Then it will take what this area is transferring to a power to the neighbor area that is sensed, that is transformed as a area control error. In terms of integral controller require error till it is 0, integral controller keep on modifying the set point. And when the error becomes 0, integral controller become idle. always integral controller must be idle. When it is idle, whatever is the previous output, that is the input for this, steadily using that. If that input is not sufficient, there must be notice of frequency deviation. That frequency deviation is taken by the error. Error must be non-zero. When error is non-zero, integral controller is in action. So error is non-zero, integral controller will make the change to the set point. When the set points are changed, the primary loop again accelerate. In this way, supplementary loop has come into picture. So supplementary loop is very necessary whenever only the primary part of the ALFC become unable to meet the frequency deviation to 0. For that, we have seen this case as the use of integral controller. So proportional integral controller has become necessary to incorporate in the path. Of course, I have not shown here what is the extra block from this. That extra block is here only. P reference point, then the integral controller of the particular frequency, and it is taken as a summer block. P reference and integral of the error, then the feedback from the group, all together modify your set point. You may ask me, what just now I have shown the block diagram, what right now I'm showing, are they same? Definitely no. This is a representation in a very simplest manner. How is that? Only frequency is taken, integral controller is situated here to see to that frequency deviation, the error is amplified, integrated, accumulated and integrated and fed as a power value here. P reference and this value is to make set point change in a very specific manner. That set point change and delta omega by R will become another correction at the input side of the governor. This was not there at that time. What was there for you? Delta omega by R and P reference were the only corrections to be taken at the summer block. Now you have this integral controller. This is trying to look for the frequency correction required immediately. Hence, need for the integral controller has come. Whenever we find a supplementary control for the ALFC, it is the integral controller role only. But here, no extra line measurement is shown. Power from the neighbor is not shown here. Just to make you aware how that integral controller incorporation makes the input to the governor or control of this block superior, was just seen by this block. Now again, I have one text page to show you how is that control works here. Let me show you that page also. I will share that also. Just a minute. That also I will show you how is that works out. Here. Am I able to show this page to you? This page is visible to you?
Yes, sir.
Yeah. So what I was speaking right now, ELFC only with the primary lobe is just somehow incomplete. In one of the best premier textbook, OIL Guard, which was one of the textbook for the previous year for your seniors and all, that explains so beautifully how these AVR, ALFC, primary, secondary loop function connected to one another in a coordinated way. That was so lucid way it explained in that book. From that book also we took some presentation in this presentation as well. So the only primary loop somehow become incomplete and fail to fulfill the requirement. Then that call for the some superior control on the primary loop so that set point is done independently. Set point control is done independently as an authority. Primary loop simply practice that set point change so that primary loop experience freedom of its play from minimum to maximum. Someone has set it as a control from the other side. That controlling is done by secondary control. Then this diagram, this page show you proportional plus integral controller. That's called secondary ALFC loop. It is seen from the previous discussion. Means in this page also has having some material. It has been put here so that we will not look forward. Whatever the controller point it is shown. So same way it is this using the material. So use of this particular proportional integral controller is to see governing system very much necessary to change the speed. It is a considerable change in frequency or increase in load, whatever the relationship we have. To address that, PI control is very necessary. Here you can see an example, and the system frequency specification is rather stringent, and therefore so much change in frequency cannot be tolerated. In fact, it is expected that steady state frequency change must be zero, error must be zero. In order to maintain the frequency at scheduled value, the speed changer setting must be adjusted automatically by monitoring the frequency changes. This is the root cause why proportional integral control is required. It is very clearly said, frequency deviations are not expected beyond a certain value. Actually, it must be, deviation must be zero. If it is not maintained zero, it is an indication that primary loop is not fulfilling the requirement. It is not failing to do. It has done its best to the max control level, but later it is not permitted to do. Therefore, to permit it to function, limit must be revised. That changing, speed changing is done by some other authority. That is the need here. So in order to maintain the frequency at scheduled value, the speed changer setting must be adjusted so that it is able to cope up to the requirement. That is being done by proportional integral controller, feeding the frequency deviation into the input block of the governor, having measured the error, magnified it, and integral of that is fed to the block here. So therefore, we can just see how that integral controller functions. The P reference point shifting of that integral of the deviation with the gain of that, taking the Laplace transform, when it become an integral part. So we had something, just I wanted to show summer block, which we had earlier. We had governor turbine block, whatever the combined representation. We had a summing block with the demand PL and mechanical input and the plant and load. And this was having a omega feedback 1 by R to the system, primary loop. This was the primary loop. And you can see a dotted line, dot, and Ki by S. What it indicates? This is the bridging up of missing closed loop. So this is very necessary. It is to indicate. It was only P reference earlier. We had only P reference, error feedback, governor turbine, and area and load delta F. That was the only block. The missing feedback was taken by integral controller. So this P reference is speed set point change. This speed set point change is done by integral controller. Integral of the error, and before which magnify the error, and integration of that makes the set point change revised in a very good way. So this revision point is going to work. And this integral controller again have a negative here. Negative, it has a meaning. Just I can say here. Why the negative you can see here. Here. For this purpose, integral controller is included in the integral controller, the frequency error first amplified and then integrated. Further, a negative sign. Can you see this? Negative sign or polarity is also included so that negative frequency deviation will give rise in command. Open the valve. So therefore, the signal fed to the integral block is referred to as area control error ACE. So ACE nothing but delta F. So therefore, this is how the necessity of integral controller has come into picture, and this made now onwards, whenever I speak of ALFC complete, it should have primary closed loop with the R and secondary closed loop with the integral controller. So in the next chapter, now I am on the verge of completion of a certain chapter now. Next chapter will include ALFC complete means primary loop as well as secondary loop. Now we got to know whenever primary loop will not fulfill the requirement, then need for the secondary loop came into picture, and integral controller bridged that gap. Then integral controller automatically shift the reference point changer, speed changer, so that governor can manage the requirement. So this way, this became a complete ALFC loop of our requirement. So therefore, I will just make this initiated in the next module, again I begin with ALFC and other things. Before closing to that, I have one more or two more problem to be discussed, because this transfer function of the plant, whichever I have seen here, 1 by 2 HS plus D, whatever I had here, on that we have some problems. One or two problem I would like to pose and I would like to complete that. For that, I have already collected the problems here, which a minute or 2 minutes I can complete it. Just a minute, I'll just try to open up and do it. This one. Hope my page is visible to you. My page is visible. It's one page I want to scroll. Is my page is visible to you all?
Yes, sir.
Yeah.
Yes,
So
sir.
now, yeah, please, just one page. I'll not take much more than 5 minutes. This is to convey you what is that area. Before I go to next chapter, there become the primary ALFC loop, secondary ALFC loop, and area of such anything will be asked you as a question. Get a transfer function of a system will be a question. The 1 by 2 HS plus D is a system representation, generator plus load. How that transfer function is evaluated. This will appear as one question in the main exam, has appeared several times. So like that, two problems I have put side by side in a single page only. You can see what is that exactly. At the end, transfer function of the system is Kp by 1 plus STP. What is this Kp by 1 plus STP? The Kp is 1 by D. Kp is 1 by D. Tp is 2H by D. If I take this conversion from this previous page, I just go back and show you. Here I had the power system transfer function. So these are the problems I wanted to even show. These are the problems. Okay, just a minute. I just show that equation and I'll go back. Where is that? Here. 1 by 2 HS plus D. This is what my requirement. Transfer function of the plant. I'm trying to get this, which is 2 HS plus D in the denominator. KPS become 1 by D. TPS become 2H by D. TPS is 2H by D here. 2H by D. 1 by D in the numerator. 1 by D. If I take to the numerator, it become KPS. KPS divided by 1 plus TPS here. That's what I am trying to show here. You can view this. Kp by 1 plus TPS or TP. So this is called as a transfer function of the generating plant. How to calculate? This is simple. Just see 4 lines of work worth 8 marks problem. It is just like this way. I read it out. Primary automatic load frequency controller loop parameter of a control area are given like this. Total rated capacity is 2000 megawatt. Normal operating load PD 1000 megawatt and frequency of 50 hertz. Inertia constant of the area is 5 seconds. Some book refer 5 seconds, some book refer only 5, some book refer like this way, kilowatt second per kVA. See how book to book this H represents change. Some book refer only 5, some book refer H with seconds, some book refer H with kilowatt second per kVA. K cancel, second remain here. Like that, there's a second description. So whatever is that, H must be given. Then areas regulating characteristics are 2 hertz per pu megawatt. So you have been given R, you have been given H, you have been given demand, generating plant capacity, and frequency of its nominal working. Then assume a linear load frequency dependency. Assume linear load frequency dependency means change in frequency causes change in load. Like that, obtain the power system transfer function. Obtain the power system transfer function. So to get this, what is the requirement? I have to obtain Kp. I have to obtain Tp. That's all. The transfer function Gp of that plant is Kp by STP. Time constant I have to calculate and Kp gain I have to calculate. For that, I have two equations. Kp is 1 by D. Kp is 1 by D. Tp is 2H by F D. 2H by F into D. To get these things, D I have to calculate. H is given the problem. Then how to get this D and split in this position, that's also a problem. Kp by 1 plus STP require Kp and TP, and TP require D 2H by FD, and Kp require 1 by D. Let's see. Load damping factor D is change in load with respect to change in frequency. Dou FD, dou PD by dou F, or it is the change in load due to change in frequency, which is, what is the load here? Load is 1000 megawatt. It is 1000 divided by 50. This is 1000 divided by 50. When I take a ratio, it give me 20 megawatt per hertz. What you get from this? The load has linear dependency on frequency, means for a change in frequency, load change. That's the nature of the text given here. Then total load divided by frequency of operation, if I take a ratio, that give me megawatt per hertz. For every 1 hertz change in the load frequency, load modify by 20 megawatt. That is a relationship. So therefore, 1 hertz change in frequency cause 20 megawatt change in the load. This is what I have to get as a D. D is differentiation or ratio of PD with change in frequency. So 20 megawatt per hertz. But you have droop in PU. Hence, it becomes necessary for me to express 20 megawatt into per unit. 20 megawatt per hertz, whatever I have, divide it by plant capacity. What is the capacity of the plant? 2000. When I make this term divided by 2000, it becomes 0.01 PU megawatt. Megawatt become per unit this time. Per unit megawatt per hertz. So this I am going to use as D. That's all. The only intelligence is how to get D. D is relationship between change in demand for a change in frequency. I have to operate. That is dou PD by dou F, like that. That will be in megawatt per hertz. Convert that into PU because you have calculation in PU. Once you do it, just see what is Kp. Kp is 1 by D, 1 by 0.01, whatever I got here. That is 100 hertz per PU. This become reverse. 100 hertz per PU megawatt is the gain of that system. So therefore, TP 2H by F into D, 2H, 2 into H given is 5, 50 into 0.01, 20 second. Then if I use this in this function, Kp is 100, 1 plus STP 20. This is called as a transfer function of the plant. So simple. This is worth 8 marks problem. You can see old question papers, it has come. So likewise, what is your notice? Load change with the frequency, converting it to PU, getting that D used in Kp and respectively in TP by relationship. This is how you can do it. So similarly, another example, I have just made it. P rated 1000, demand as 500. Demand I made 500, capacity I made 1000, H I made 4, R I made 2.5 hertz per PU megawatt. And you can calculate. So dou P by dou F, 500 divided by 50, 10 megawatt per hertz. Divided by the power of a plant, it becomes 0.01 PU megawatt per hertz. Then TP, Kp calculation. 2H by FD, 2 into 4 divided by 50 into 0.01, 16 seconds. And Kp is 1 by D, it becomes 100. So this is a plant equation.